through this pretty quick, but it's better to spend the time on the actual calculus concepts. Another thing that we should have a sense of is inverses, what the inverse of a function is. You learn this in grade 11 and you look at it in grade 12 as well. The inverse of a function. Just intuitively, the inverse of a function, if you go back to your calculator here, different things that are inverses are grouped together, right? Dividing and multiplying, those are inverse operations. Plus and minus are inverse operations. Often inverse operations are on the same button, x squared and square root. Sine and sine inverse, it's even called inverse. Logarithm and anti-logarithm here. And then base e, same thing. If you take any function here, like what we have over here, x plus 2, that function takes values and adds 2, right? This is adding 2. So its inverse is subtracting 2, right? The way you undo this, subtract 2. This one undoes this one. They cancel each other out. Okay, I mean, I'm writing it again, but it's over here, right? To say it in the kind of everyday way. If the two functions are composed, they cancel each other out. That's a good thing to realize, that if you make a composition of f and f inverse, you've seen this notation before, right? F inverse with the little negative 1 there. You don't say f to the negative 1, you say f inverse. It's maybe not a good choice, whoever chose that negative 1 as inverse, because then we get mixed up with reciprocal and all the problems that you have in grade 12 with those, getting those confused. The inverse of a function and the function itself cancel each other out. If I take these two functions, f of f inverse of x, and compose them together, we'll see what does it turn out to be if they cancel each other out. If I compose the two functions together, f of f inverse. Oh yeah, it gives you what you started with. If I take an x value, just think about it with numbers here. Let's say I take the number 7 and I apply f of x to it. What do I get? I get 9, right? Because it's adding 2. And then if I take f inverse of x and I apply that, it's subtracting 2. What do I get? You get the 7 back again, right? You get your original value back. All right, you start with 7, you end with 7. So it makes sense that if I start with x and I apply f of x, I'm going to get x plus 2. And then if I apply g of x, what do I get? Sorry, I called it g of x here, but we'll be consistent, right? F inverse. If I take f inverse, I apply f inverse of x, what do I get? You add 2, then you subtract 2, you're going to get x again. So if you compose the two functions together, if we're putting this together, we're starting with an x, and f of x is x plus 2. So then we're going to do f. Actually, I'm putting minus 2 inside because I'm putting the inverse function inside. That function plus 2. If you compose those two functions together, x minus 2 plus 2, I just get x, right? This should turn out to be x here. If the functions are inverses, then they'll cancel each other out like that. And if you do it the other way as well, I want you to try for these, at least one of them. Maybe not part C, because that's a little bit of fiddling around, because the x is more than one place there. But let's say for this one, find the inverse. Do you remember how to find the inverse from grade 12 or grade 11? If it's going to undo it, right, you switch x and y. if I take this function then and change it around here, the inverse is going to be if you switch x and y. If I change this to x equals 2y minus 3, on a graph, the inverse is reversing the coordinates of a point. It's reflecting over a diagonal line. Okay, so try that and then confirm. You hopefully successfully found the inverse there. Switching it around and then isolating the y. That's how you're going to find it. So if you switch it around and then just proceed to isolate the y. So you have 5x is equal to 2y minus 3. And you have y is 5x plus 3 and then divided by 2. We should probably call this one f of x because it's the original function. Is that what it's called up there? And this one is then going to be called f inverse. F inverse of x is 5x plus 3 over 2. If you want to confirm or show that they're inverses, you take this and you take this and you show algebraically that they simplify to give you x. Okay? Not, you could test it just by putting in a number, right? You could try putting in a 3 or a 7 or some number in here, seeing what you get for y, and then confirming that the reverse works. But to prove that they're inverses, you have to do it algebraically and combine them together. So if you take f of f inverse of x and just confirm that that's equal to x, you can show that they're inverses. So I'm going to take f of this inverse, 5x plus 3 over 2. So that's this, right? That's f inverse. And I want to put in there, I want to put that into the other function. I want to put that into f. So I'm going to go 2 times that minus 3 over 5, right? And we want to prove that that's equal to x. You know, you did proofs in grade 12, trig proofs, kind of the same thing here. So I'm taking this function and I'm replacing the x, right? I'm composing the two functions together. I'll leave this one as 5x plus 3 over 2. If you work your way down there, they should simplify, right? You can simplify the 2's, right? If it's a proof, you should probably show every step there. I know you can do the whole thing in your head, but you probably should show every step if it's a proof, right? Just like I did in. Okay, if you want to show that they're inverses, that's how you can do it algebraically. If you want to show that they're inverses graphically, if you were to graph those two things, there'll be reflections across that diagonal line. There'll be reflections across this line. You can graph those sometime to confirm that for yourself. Any questions about that?